This meeting is being recorded.
In problem 8 from chapter 12, we are asked to identify what reagents could be used to accomplish each of these transformations. So we'll take a look at each of these questions, and we'll begin with an analysis of our starting material and then our product here. So in our first example, we have an alkyl halide, that is our starting material, and our product is an alcohol. So we should know that we can use a substitution reaction to accomplish this transformation. And since our substrate is a tertiary alkyl halide, we would know that this reaction specifically would be an SN1 mechanism. So far we know that we have a tertiary alkyl halide would follow an SN1 mechanism for our substitution. And we know that a weak nucleophile would have to be used to favor a substitution. So something like water could be used as our reagent here, or else if we used a stronger base, so I'll put an X here, so we can't use sodium hydroxide, or else an E1 elimination mechanism would be favored. So no strong base, right? We don't want an elimination, we want a substitution. So let's look at part B here. So again, our starting material is an alkyl halide. In this scenario, it is primary. So we know that with primary, SN2 mechanisms can give us our alcohol product here. And in this case, we can use a strong nucleophile, such as something like hydroxide. So sodium hydroxide could be a reagent that we could use to accomplish this, this transformation. So on our third example here in part C, now we no longer have an alkyl halide, we have an alkene. So for part C, we would have to perform an addition reaction to form our alcohol product now. So our OH group has to be installed at the more substituted position. So we need a Markovnikov addition, right? This carbon here, we have that OH group installed, and then down here, the hydrogen. So we know that we need Markovnikov addition of our H and our OH. So that could be accomplished using something like an acid catalyzed hydration. So we could use dilute H2SO4, H2SO4 for our reagent there. Let's take a look at D. So in part D, again, we have an alkene and our product is an alcohol, but now we have installed the OH at the least highly substituted area. So we know, again, we need addition to form our alcohol product, but we need an anti-Markovnikov addition. So reagents that could accomplish an anti-Markovnikov addition could be through hydroboration oxidation specific reagents. So we could have our two-step mechanism here. We could use our borane in tetrahydrofuran, THF, and then we could follow that up with hydrogen peroxide in basic conditions. So we could do H2O2 in NaOH for D. And then we have E here. So we have, again, an alkene. And now I see installation at the more highly substituted position here. So we have Markovnikov addition of H and OH, but we might have carbocation rearrangement concern. So we want to install our hydroxyl group here. So what's preventing a methyl shift from occurring and then installing the hydroxide on a tertiary carbocationic site? Well, if we did a oxymercuration, demercuration, that would solve our problem. So we can use oxymercuration, demercuration reagents. And that would be something like our mercuric acetate and in water. in step 1. So this will be our first step reagents. And then we need a reducing agent, something like sodium borohydride could be used. And so these will be our reagents for part E. So we need to ensure no carbocation rearrangements and then have a Markovnikov addition. For part F, our starting material again is an alkene, and we see our products in alcohol. What happens is an anti-Markovnikov addition. So the hydroxyl group is installed on the least highly substituted carbon on the left-hand side. So that's what we see here. So our reagents, again, could be through hydroboration oxidation. So we would have the same steps used as in example D here. So we have borane, tetrahydrofuran, and then we could use hydrogen peroxide in basic conditions.